previous lectures, if you recall, we had talked about the different number systems, binary, decimal, octal and hexadecimal, and also we showed how to convert one number system to the other, and also with respect to some examples we illustrated how we can represent numbers both positive and negative in binary, and also carry out some arithmetic operations like addition and subtraction. Now, there are some applications where the primary numbers that we want to manipulate on are decimal in nature. You take an example of a payroll application where the employees' salaries are calculated. So, in those kind of applications there is very little arithmetic or calculations involved. See, when you have very heavy calculations, then it makes sense to convert the numbers into binary, because binary circuits are much faster. Binary adders, subtractors, multipliers are much more efficient to work on numbers. But when you have such decimal numbers, there should be some alternative so that we need not have to convert every time into binary and back, because there is very little calculation in such kind of applications. Mostly we will be doing some reading from a file and printing, stuff like that. So, in today's lecture we shall be concentrating on precisely that. So, the topic of the lecture is BCD and Gray code representations of numbers. So, let us see what the idea is. We start with something called binary coded decimal numbers. Now, as I had said that it is sometimes desirable to manipulate numbers in the decimal number system directly instead of converting them to binary. Why? The reason is very simple. We had seen that of course, we can do decimal to binary and binary to decimal conversion, but these conversion processes are not very trivial. We will have to do either repeated multiplication or repeated division to carry out the process. So, instead if we have an alternate representation where we do not have to make this conversion, do not have to carry out these multiplications and divisions, then it would be very efficient in terms of the overall computation. So, what we talk about are something called binary coded decimal or BCD. BCD is the acronym for binary coded decimal. So, what is the idea in BCD? Here every decimal digit is represented by 4-bit binary equivalent. So, you can say if I have a k digit number, then each of the digits will be represented by 4 bits. So, you will be having finally 4 into k, that many bits. This is the basic idea. So, here are some examples. Suppose I have a decimal number 238. So, if you want to convert it to BCD, you convert it digit by digit. 2, the 4-bit binary equivalent is 0010, 3 it is 0011, 8 it is 1000. So, this is your BCD representation. Talk about a number with decimal point, let us say 12.39, 12, 1 and 2, 1, 2, then the point 3 and 9. So, you see the conversion is 1 to 1, straightforward. Just the only point to note here is that we are talking about the numbers 0 to 9, which are the decimal digits, and we are converting them into 4-bit binary. Now, you recall in 4-bit binary we can represent 2 to the power 4 or 16 distinct numbers. So, out of them we are using only 10, the remaining 6 we are not using, right. So, which 6 combination? These 6 combinations we are not using: 1010, 1011, 1100, 1101, 1110 and 1111. These 6 combinations we are not using in case of the BCD system, right. So, let us move on. So, here you see the 10 decimal numbers digits 0 to 9 and their corresponding 4-bit binary equivalents. Now, as I said, the remaining 6 combinations which corresponds to 10, which is 1010 up to 1111, these are not used in this case, right. So, this is something you have to remember. Now, next let us see, we said that the advantage of BCD is that we can convert decimal numbers into BCD coded binary representation very easily, that we had seen how. Next is, if we want to do some simple calculations, let us say some additions, how do we do it? Directly in BCD. So, now we shall be talking about some rules for addition of BCD numbers. See, the rule is fairly simple. When you see that when you add BCD numbers, there may be some correction steps we may have to go for. There can be some correction steps. Now, in the correction steps, what we do? We may have to add 6, which in binary is 0110 to one of the nibbles. Now, the rules are very simple. When do we do the correction? We do the correction if either one of the nibbles is corresponding to an invalid combination, which means that the combination from 10 to 15. So, the one of those 6. So, if it is one of those 6, it is an invalid combination, then we apply the correction step. Or there is another alternative, if there is a carry from the previous stage, from the previous nibble, then also you carry out this correction. Let us look into an example to illustrate this point. Fine. So, here there are 3 examples which are worked out. Let us look at the first example here. So, here we are adding 23 and 46. So, you see 23 we have coded in BCD like this 20010 and 30011. 46 we have coded like this, 4 is 0100, 6 is 0110. Now, when you add, you see bit by bit we follow the same rule for binary addition. 1 plus 0 is 1, no carry, 1 and 1 is 0 with a carry of 1, 1 and 1 is 0 with a carry of 1, 1 0 0 is 1, no carry, all 0 0, 1 and 0 is 1, no carry, 0 1 is 1, 0 1, no carry, 0 is 0. So, you see after this addition, both these nibbles are valid decimal digit, BCD digit. This is 6, this is 9, and also there is no carry from one stage to the next. So, none of these two correction conditions are true here. Therefore, whatever you got here, this is our final result. You see 69, 23 plus 46 is 69. Fine. This is one example. Let us take another example where one of the nibbles become invalid. Take an example 23 plus 48. So, this is 23, 2 and 3, and this is 48, 4 and 8. So, let us again add 1 plus 0 is 1, no carry, 1 and 0 is 1, no carry, all 0, 0, 0 and 1 is 1, no carry, all 0, 1 0 is 1, no carry, 0 1 is 1, no carry, 0. So, you see here there is no carry from either this stage to here or carry out from the final stage, but one of the nibbles here, this one is invalid 1011. 1011 is an invalid combination in BCD. Okay? That is why we apply a correction step on this nibble, we add 6. We add 6 again following the rule of binary addition. 1 and 0 is 1, 1 and 1 is 0 with a carry of 1, 1 0 1 is 0 with a carry of 1, 1 1 0 is 0 with a carry of 1. So, now there is a carry coming. Okay. So, this 1 and 0 will become 1 1 1 0. So, you see the result is coming to 71. This is 7, this is 1, which is 23 plus 48. So, the result is coming to correct. Now, take another example, let us say 28 plus 39, we take this example here. This is 28, this is 39. Let us do the addition again, 0 and 1 is 1, 0 0, 0 0, 1 1 is 0 with a carry of 1. You see now there is a carry coming from here to here. This 1 and 1 is 0 with a carry of 1, 1 1 1 is 1 with a carry of 1, 1 0 0 is 1 0. So, you see after addition the nibbles are both valid, 0 1 1 0 and 1 0 0 both valid, but there was a carry here from the first nibble to the second. So, you add a correction step 6 here. So, after addition this will become this, which is 67, 28 plus 39 is 67. So, now you understand these are the simple rules for BCD addition. So, whenever we have such BCD numbers, you simply just add the numbers first in binary, then see either one of the nibbles are becoming invalid or there is a carry. Well, if either of the condition is true, then you add 6 to one of the digits. Now, here the example I have taken applies to the first nibble, it can also happen to the second nibble, then also you will have to do the same thing, right, you will have to add 6 to it. So, the rule is like this. Next, let us talk about another kind of code using which also you can represent decimal digit, not only decimal digits, any binary number, any multi-bit number you can represent in gray code. Now, let us try to see why we need gray code first and what is the basic reason that we are moving to a new code. Okay. Let us first talk about the conventional number system. Like when we talk about the numbers, let us say in decimal 0, 1, 2, 3, etc. So, when you write the representations in binary, let us say 4-bit representation, 0 0 0 0, 1 is 0 0 0 1, 2 is 0 0 1 0, 3 is 0 0 1 1, 4 is 0 1 0 0 and so on. Now, the issue is, let us see from one combination to the next, how many bits are changing. Let us look at that. See, from 0 to 1 only the last bit is changing. So, only one bit is changing, 1, but from 1 to 2 both the last 2 bits are changing. So, there are 2 bits changing. 2 to 3 again only last bit only 1, but 3 to 4 you see all the 3 last bits are changing, it is 3. Now, there are many applications we shall be talking about where it is good if you can reduce the number of bits that are changing between successive counts. If multiple number of bits are changing, there can be a problem. We shall take an example and show how that kind of problem can come, but for the time being assume that if multiple bits change there can be a problem. So, we are trying to avoid that. We are trying to come up with a counting system where only one bit is changing across successive count values. Okay? This is what we are trying to do. So, let us see what is a gray code. The first thing about gray code is it is non-weighted, means unlike binary numbers where every bit position has a weight 2 to the power 0, 2 to the power 1 like that. In a gray code number the bit positions you cannot assign any weight like that, and any And the second important thing which I have already mentioned, that successive code words differ in only one bit, and any code where this property holds, where there is a 1 bit difference between successive words, is called a cyclic code. So, gray code is a cyclic code. Now, the second part I shall be explaining a little later with the help of an example, but for the timing let us assume that for any application where you need to convert from analog to digital means say any value which is continuous in nature, like you think of temperature, you think of motion, you think of the rotation of a wheel, these are all continuous events. So, you cannot say that I will only rotate by 1 degree, 2 degree, 3 degree, I can rotate by 1.5 degree, 1.2 degree, 1.15 degree, anything I want, right. It is a continuous motion. But when you want to represent this kind of a continuous quantity or parameter in binary, so there has to be a mechanism for this conversion, alright. So, if you convert it into 4 bit representation, then you can have 16 possibilities. Suppose the rotation of a wheel you are representing in 4 bits. So, you can have 16 possible rotation angles, because in 4 bits you can represent 0 to 15. But if you represent it in let us say 8 bits binary, then you can have 256 rotation angles that you can represent. 2 to the power 8 is 256, right. So, gray code is useful here, and this point I shall be explaining why it reduces error in conversion. This I will explain a little later. The second thing is that it is fairly simple to convert a binary number to gray code or a gray code number to binary. We shall also see through example. So, this example of a wheel we shall be seeing later and explaining these points with respect to that. Let us talk about a 4 bit gray code. This table shows a 4 bit gray code and also the corresponding binary representations. The first column shows the decimal numbers 0 to 7, 8 up to 15, and these are first the binary representations. So, as I have already seen 0, 1, 2, 3, 4 up to 15. Side by side we have also shown the corresponding gray codes. These are the gray codes for this decimal number. 0 is represented as 0000, 1 as 0001, 2 as 0011, 3 as 0010 and so on. You see, between any pair of codes exactly 1 bit is changing. Let us say if you consider these two, last bit is changing. If you consider these two, the second last middle bit is changing. So, between any pair of bit patterns you see here, take let us say this and this. So, here also the middle bit is changing, exactly 1 bit change. Similarly, from 15 back to 0 only the first bit changes. This is what gray code basically is. So, across successive codes exactly 1 bit positions change their states, right. This is one property we mentioned of so called cyclic codes. This is an example of a cyclic code, all right, fine. There is another interesting thing about gray code, for which it is also sometimes called self-reflecting code. Now, the idea of self-reflecting code is like this. Suppose I have my gray code representation for 4 bits. Now, I want to have it extended to 5 bits. I want to have a 5 bit gray code representation. Now, from 4 bits it is very easy to convert it into 5 bits. From 5 bits it is very easy to convert it to 6 bits. This is the basic idea, and such codes is sometimes called self-reflecting code, for a reason that we will see how. The idea is very simple. Suppose I have an m bit representation, I have m bit gray code representation already available with me. So, I am showing it as a box. Let us say this is my m bit representation. What I do, I write down that m bit representation again, not directly, but as a mirror image. The last number goes first, the first number goes last. That is called self reflecting, as if it is reflecting. And in the first segment, I am adding a bit 0 in the beginning, and in the second segment, I am adding the bits 1 in the beginning. So, I get the gray code for m plus 1 bits. This is the basic idea. So, see what he mentioned. To obtain the gray code representation for m plus 1 bits, we write down two m bit representations one below the other, just like I showed, with the second one being the mirror image of the first one. It is just the mirror image. Then we add 0 in the beginning of every code in the first block and add a 1 at the beginning of every code in the second block. So, let us take an example, this one. Suppose I have a gray code for 2 bits, this is the gray code representation 0, 1, 2 and 3. So, when I want to generate the gray code for 3 bits, you see I write this twice, first as it is, second as a mirror image. Mirror image means 1 0 comes first, 1 1 next, 0 1 next and 0 0 last. Then I add zeros in the beginning of the first block and 1 in the beginning of the second block. So, I get 3 bit gray code. You see, check here, across every pair of codes exactly 1 bits are changing, 1 bit is changing. Similarly, from 3 bit to 4 bit you follow the same principle. You write down the 3 bit gray code block twice, one the mirror image of the other, same way, just reflecting, add 0 in the beginning of the first block, add 1 in the beginning of the second block. So, what you get is 4 bit gray code. So, generating gray code from m bits to m plus 1 bits is fairly simple, as you can see, right. So, this is also a reason why it is called self reflecting code. Now, let us look at binary to gray code and gray code to binary conversions. First, let us look at how we can convert a binary number to gray code. Let us consider in general that we have n bit representations. Suppose my binary number is represented like this, b0, b1 up to bn minus 1, and the corresponding gray code number will be g0, g1 up to gn minus 1. The rule is fairly simple. The most significant bit is straight away copied, okay, this should be b, read it as b, right. So, gn minus 1 equal to bn minus 1, the most significant bit is straight away copied, and for all other bits you take the modulo 2 sum, this is called modulo 2 sum of the corresponding binary bit and the next most significant binary bit bi plus 1 for all other values of I, this is I, right. This is the rule, and this modulo 2 sum is defined as follows: 0 modulo sum 0 is, sorry, this is 0, this is 0. Just a second, yeah. So, what I said is that this is actually b and this is actually 0, and 0 modulo sum 1 is 1, 1 modulo sum 0 is 1, 1 modulo sum 1 is 0. Now, when you convert, there is an example, let us say 101 is a binary number. The most significant part 1 you simply copy here. The next bit of the gray you take as the modulo 2 sum of the corresponding binary bit and the previous one, this 0 and 1. 0 and 1 modulo 2 sum is 1, it becomes 1. The next bit is 1 modulo sum 0, this is also 1. 1. Next bit is 1 and 1 0. Next bit is 0 and 1 1. Next bit is 1 and 0 1. Okay. Let us take another example. Suppose I have a binary number 0 1 1 0 1 0 1 0. Let us say an 8 bit number. So, let us follow the same rule. The first bit is straight away copied 0. The next bit will be the modulo true sum of this two previous bit 1 and 0, this is 1. Next one is 1 and 1, which is 0. Next one is 0 and 1, which is 1. 1 and 0, which is 1. 0 and 1 is 1. 1 and 0 is 1. 0 and 1 is 1. So, this is the corresponding gray code representation of this binary number. So, given a binary number, you can very easily convert it into gray code, right. Okay. Let us look at the reverse, gray code to binary number conversion. Well, the rule is fairly simple, as you can see. So, we start with the leftmost bit position and move towards the right, and the rule is the binary bit is said to be the same as the gray code bit if the number of ones preceding GI is even, and we set it to the complement. This GI dash indicates it is the complement, okay, the complement of that complement if the number of ones preceding GI is odd. Okay. Let us take an example. Suppose I have a gray code, let us say 0 1 0 1 1 0. Let us say, let us take an 8 bit representation, 8 bit gray code, and I want to convert it to binary. So, when you move to the first bit, there is no preceding bits. So, number of ones preceding this is 0, which is even. So, I simply copy bi equal to gi, this 0 gets copied. I move to the next one, number of preceding 1 is still 0, even. So, I straight away copy, this will be 1. Then I come to 0, the number of preceding ones is 1, which is odd. So, it will get complemented, 0 will become 1. 1, number of preceding 1 is again 1, which is odd, this will get complemented. 1, number of preceding 1 is 1 and 2, it is even. So, it will be straight away copied. 0, preceding 1 2 3 odd, so it will get complemented. 0, again 1 2 3 odd, it will be complemented, and 1 1 2 3 odd, this will also get complemented. This will be the equivalent binary number for this. So, you see conversion is not that difficult. So, if you know the rule, you can straight away convert it like this, fine. Okay. Now, let us talk about that example that we are talking about, that means why we say that gray code can reduce errors. Well, let us take that example of a rotation of a wheel. Look at this diagram. There is a wheel, let us say it is the wheel of a car or any kind of a mechanism which is rotating, and you are trying to measure or monitor the degree of rotation of the wheel. So, what we do on the wheel, on one place we drill some holes, and on one side there are some light sources, and on the other side there are some light sensors. So, whenever those holes come under the light, so if there is a hole, light will pass and the sensor will be sensing it, and if there is no hole, there will be no light and the sensor will not find any light. Okay. So, it is something like this. There are some light sources, as you can see on one side of the wheel, they are arranged like this, 5 of them are shown, and on the other side there are some sensors, these are some light sensors. And the wheel we are coding like this. You see, some part of the wheel is shown as white, some part of the wheel is shown as colored. The idea is colored means they are opaque, they are solid, light cannot pass through it, and white means they are transparent, maybe they are made of glass, light can pass through it. and the way we have made this coloring and whitening is based on the gray code. Let us take an example of 3 bits. These are the 3-bit gray code representation. So, the successive numbers we have written down 000, 001, 011, 010 and so on. And if it is 000, you see we have made it all white, white, white. So, white means 0, solid means 1. 001 is 001, the 1 is solid, 011, 011, 010, 010, 110, 110, 111, 111 and so on. Now, because it is gray code, so across one segment and the next exactly one of the bits are changing state. Now, imagine if we did the same thing with respect to binary. Think of the binary numbers, let us say in 4-bit, consider the number 7 0 1 1 1, next number is 8 1 0 0 0. So, all the 4 bits are changing. So, now imagine if the wheel is just between 7 and 8, just it is moving. So, some of the lights may be passing, some not passing due to some alignment, there can be a little error, some of them is sensing, some of them is not sensing. So, in the worst case there can be an error of so many bits because all 4 bits are changing. But in gray code, because only one bit is changing between one segment to the next. So, during the transition even if there is a small error, only that one bit can be either 0 and 1, other bits will be very stable. So, the error can be at most in a single bit in gray code during this rotation sensing, right. This is the main idea behind using this kind of gray coding. In this is just one example I have cited, there are many other examples. Like here I am just mentioning one example that in the design of circuits we shall see later when you talk about sequential circuits, we shall see that if we use some kind of gray code encoding, then between successive states when some signal is coming, if we ensure that only one of the outputs are changing state at a given time, then it can provide us with a mechanism with which we can reduce the amount of power dissipation, because power dissipation or energy dissipation is very important nowadays because most of our devices are working on batteries. So, minimizing power is very important and this gray code encoding also helps in that, all right. So, this is what I mentioned, if binary code was used instead of gray code, multiple bit position might be changing across segments and so the error could have been higher. But in gray code you can have only in a single bit position during reading. Okay. So, with this we come to the end of this lecture. Now, in the lecture number 6 we shall be talking about something else. We shall be talking about error detection and correction. So, in binary we have represented some numbers, they might be stored or they might be communicated from one place to the other. There are chances because of various reasons that some bits may get flipped or erroneous. So, how to detect and correct them, that will be the topic of our next lecture. Thank you.